Thank you. Can you all hear me at the back? So I'm not going to stay at the podium. I'll come up front a little bit. First of all, thank you so much for having me. It's an absolute honor. I've only been to Institut Pasteur once before, and I'm going to be here for the next couple of days. I am on my route to a clinical trial in Senegal, so I actually happen to have lots of tools with me that we use in the field. So although we don't have enough time to do demos right here, right outside, find me. We can spend lots of time thinking and talking about these sets of tools. And I'm going to start my clock just to be on time. So I think I often struggle with time, so I'll start with acknowledgements first. I just want to say that was a very kind introduction, but I want to make sure I don't work alone. There's a remarkable group of young people, individuals, students, postdocs. Many of them now have their own labs around the world. And it's really a pleasure, and many collaborators that you'll hear about that make something like this possible. The thing that I do want you to take away is two very simple messages. You know, every threat that you saw and heard about, what you will hear about in this, the next couple of days, these are multidimensional threats. And there are two key messages that at least I shared when I'm thinking about. One is really, at the end of the day, curiosity and basic science is the primary way to attack some of the most complex problems that our society is facing currently. And then the other one is a little more subtle. I teach this class called Frugal Science. It's a global class, anybody can take it, and it's really about solving problems with cost as a framework in mind. And every year I have students around the world, and last year I had a student from Sudan, Marwan, and we spent 6 months together. This is right before the war. And I asked him, you know, what does this class mean to you? Why are you here? And he said, Manu, we have this saying in Sudan, don't create a pen that doesn't eradicate ignorance and shame. And it kind of dawned on me what he was trying to imply. Pen is a pinnacle of technology. And often enough, technology by its own sake might not lead to the answers that you might be looking for, or even as a creator of a technology or the sets of tools. Unless they reach people, unless they reach the right set of people, unless they reach them in the right set of circumstances. So much of the examples that I want to give you is examples of programs we have started, with technologies we developed, but community programs that were built around these sets of tools. So now, if you get bored, you could do other things. These are the only two things that I really wanted to tell you. Okay, so let's start with a few sets of examples. How did I get my start into this? You know, I love the living world. You know, I know all of you, even though many of you work on parasites, they're pretty clever. I mean, they just do beautiful things. And you have to be honest about this. Ironically, you know, on our planet, we really don't understand much of the life on this planet. It's just remarkable to think about. By all kinds of estimates, majority of the life is still yet to be discovered. It's microscopic. Now, how ironic to be on this planet with that statement being true, while on the other hand, if you think about the state of how we teach life science, and I'm going to spend majority of my time talking about education because that's very important. Out of 2 billion kids on this planet, 1.2 billion live under poverty. That's half of the talent that will never have access to even the philosophy of thinking about science. If you think about 500 million kids that went through school like what's shown in that picture with the tiny little cell phone, you start realizing what a big impact it had on the sets of trajectories. And a personal experience for me, which I will always remember in high school growing up, I was given an exam where you're supposed to draw a microscope. And you see, microscopes have played a big role in my personal life. And I was supposed to draw it exactly as it was drawn in the book. Neither me or my teacher had ever seen a microscope. And if you were to draw it from another perspective, you wouldn't get the right answer. So you should have read the right book. And that's the harsh reality of what we think about experience of science. You know, often enough, we throw books at people. We think about, here is a stack of knowledge. But unless any one of you would not be here until you'd actually experience the aha moment yourself. And that started kind of a thread on the back of my mind, which I'll come back to in a second. I think I talked about education. That's one of the pillars of the work we think about. But if you start asking now these same sets of challenges in the context of ecology, we're facing a tremendous, like literally right under our feet, much of how the ecosystems are organized are starting to shift. I don't have to tell you this. This is an apocalyptic paper. I still don't believe we actually understand how we have lost such a majority of insects around the world. When you start thinking about healthcare, which many of you work on, this is a picture that I took in Ghana of a malaria clinic that gets popped up every time. And roughly 1 billion people still would say that the care that they get delivered to is actually through pop-up clinics around the world and primary health centers. For some of the sets of challenges, and malaria will talk a little bit about that very specifically, these sets of challenges are also escalating. Some of you have heard about this, but the new sets of pathogens and vectors that are at place. And often enough, this is compounded by many of the other environmental factors that we were not measuring. One of the ones that we were not measuring is sets of plastics in our environment, where we really don't even have a link between what we do in our environment and the sets of medical problems that we are about to face in the future. There is one that I want to mention very specifically, which has to do with global warming and climate change, because this is something, it's ironic to be in a meeting where there is global health and climate change. We actually work on these sets of problems in separate domains because we spend a lot of time building frugal tools to directly measure carbon sequestration in the ocean. And I want to be the bearer of more bad news to the table. Very recently, we published a paper this week that shows that the methods that we have been using to actually directly measure sequestration in the ocean actually has a major error on the wrong side. So this would account for roughly a miscalculation of 40 parts per million, or roughly around 100 gigaton of carbon. So we're on a planet, and for some of you biologists to care about, that error actually comes from a microbial process. It's how bacteria produce polysaccharides that essentially reduce the sinking dynamics of much of the carbon in the ocean. Because many of the earlier models never included any biological terms, you're bound to find completely new phenomena, completely new non-linearities that exist in the system that put many of these sets of things on shaky ground. So, I think I'm hoping that by this time you're all depressed, and this would be the most depressing talk that you've heard. But I lose a lot of sleep, and I want you to lose a lot of sleep, because unless we're honest with the problems that at least we face on the ground around the world, we won't be off on a good start. But having said all that, I think there is a narrative that's out there that's often tossed around that, oh, is technology the answer? And I don't believe that personally. Technology plays a very important role, but of course, access and being able to get that technology in hands of people that need them the most is really the right answer. So in the last few, the next phase of this talk, I want to share a slightly hopeful view of what I talked about exactly in these 3 sets of disciplines: in education, in environmental context, and actually in global health tools, to see what does it mean to build programs and build sets of technologies where access is actually embedded in the design of many of these tools themselves. So that sounds like a big challenge, because for most of the time, if you were talking about access, you really have to be thinking of a planetary scale. For every problem that I told you, it doesn't make a difference unless you start with the planet as a whole. And often, we don't even have enough scientists to begin with. We don't even have enough doctors to begin with if you start thinking about community health programs. So it also means an acknowledgement that we're going to build a much more inclusive environment where many sets of tools and technologies and the definition of who a citizen scientist and a community health worker are part and parcel of the sets of solutions we're about to build. We do this with a framework and a philosophy that we've been calling Frugal Science, where cost comes at a very critical design phase from the early set of starting to build these sets of tools and examples. And we're not the first one to think about this. That's interesting. I was about to ask you what you see on your screen, And then the screen disappeared. Okay, I'm going to try not to touch the cable. Anybody recognize this object, by the way? Sputnik, exactly. It also sometimes tells the age of the person who identifies it. But it's important because this was a remarkable object. It inspired literally billions of people on this planet when it was launched. But I don't know how many of you know this. We did not know whether somebody has launched a satellite successfully or not at that time. It's like diagnostics. Space is pretty big. Anybody could claim that you've launched a satellite and you wouldn't know. And at that time, Fred Whipple, an incredible astronomer, came up with an idea. What if he distributes telescopes to literally tens of thousands of people around the world? That led to what is called Operation Moonwatch. At that time, it was the world's largest citizen science program. And these individuals are the ones, not the government-funded, centralized telescopes that were out there. These individuals identified every other Sputnik that was actually fired. For the next 60 years, it set the stage for what really became astronomy. The only supernova that has ever been seen has been seen by an amateur astronomer who was just testing a new camera on his rooftop. That's the only direct visualization of a supernova. So when you start thinking about these sets of tools and you ask, what does it mean when you can distribute technologies on a global scale? You know, for me, when I think about citizen science, I think about a community health worker. This is a picture from Last Mile Health. This is a community health worker that's about to head out into a clinic or a village that has a potentially reported case of Ebola, for example. And many of the tools and examples that I want to share with you are things that would go in that backpack. And our job should really be as enabling brave individuals like them at the frontier of what you can call an emerging infectious disease to be tackling those sets of diseases. So I'm going to give you a few examples now. You know, I've been doing this 15 years now, so I spend a lot of time in the field. And I remember as a young assistant professor, I had a bright idea, and I went to Uganda. I was spending some time with some doctors, and an individual there who's been teaching and training for the last 30 years said, Manu, you should come back to me when you can do diagnostics under a tree. And he had a point. You know, many a times you meet the disease and pathogens for the first time, literally right under a tree. And I'll give you that actually after 15 years, we can do diagnostics under a tree. And often enough, although I said many depressing things, you should remember that bicycles were invented primarily because of a volcano that had caused a massive famine that led to the sense of creativity and invention. So there is, in the context of thinking about these sets of challenges, a silver lining, that the way we approach and the approach that we invent through this crisis might actually lead to solutions that last for a long time. Okay, so enough of that. Let's talk about a few sets of solutions. I want to give you very concrete examples. Much of the work that I'll talk about is published, so you can find many of the greater examples. And I also keep looking at the clock, and you will see I talk exponentially faster as I keep getting to the end of the talk. So find me afterwards if you're looking for certain sets of details. We've been building almost dozens of tools. Many of them have hardware as a context, but many of them interface in these sets of examples. And I'm going to just cherry pick a few examples to share with you. So just in COVID itself, one of the key things that we focused on was a lot of life-saving technologies that were really packaged as medical devices. One challenge that you all know in medical device manufacturing is a pretty difficult task to ramp up. And in a short period of time, we built an ICU-grade ventilator that was completely open source. It was really designed like a web browser, some of the original web browsers that led to the blueprint for all the web browsers that we use today are actually all open source. And one of the challenges that we tackled is we work with partners, this is 3 countries, India, Nepal, and Kenya, to essentially in 7-month period of time, ramp up a complete manufacturing facility. And the reason I'm just sharing this story, it was very interesting that the partner that we found in India was actually a defense manufacturer. They knew how to build rocket engines. That's what they were building before, but they had never built a medical device. And so it's not as if knowledge is not there. It's not as if technical capabilities are not there. It's just that certain amount of hand-holding is required when you enter in a new domain. And this has been a phenomenal partnership because now they have actually built a biomedical division as part of the sets of technologies that they're starting to serve and bring out to the market. Let me share one example for something that I've spent almost now 15 or 12 years of my life, which is foldscope. How many of you have actually used or know what a foldscope is? Okay, so that's maybe 25%, so I will spend a few minutes on this. You know, the challenge for us was we started thinking about microscopy. I was obsessed with microscopes. When I grew up, I started building them, but we put ourselves on a challenge. Could you watch a single bacteria, so between, 600, 700 nanometer resolution, for a price point of $1? That was the goal. We spent a lot of time, 6 months, just doing math, and ended up actually solving the fat length equation, which is down there, that led to a capacity that we can, from a piece of paper, literally this object that you're seeing, we can now do microscopy. So we call these foldscopes. This is an origami microscope. We invented this somewhere around 2013, 2012, published a paper. I was very proud of it. But I don't know how many of you have had this feeling. When you publish a paper, it shows up online, either on bioRxiv or arXiv or some journal. And you wake up the next day and nothing in the world has actually changed. Literally nothing has changed. And you wake up and you realize, wait a second, is that it? And, to add a little salt to the wound, there was a gentleman there whose name you can read. He read our arXiv paper, and he tweeted about it. And he said this, a $1 origami microscope, ? Interesting, ... And what I was stuck with was the question mark. Why did he add a question mark? Did he not believe that we had done this? And actually, it dawned on me at that point that no, unless we start a program, it means nothing. So at that point, we decided we are going to ship around 100,000 microscopes. Anybody in the world who asks us, we will ship. I spent $250,000 of my startup money shipping these 100,000 microscopes, Congo, Iraq, everywhere in the world, every aspects, no questions asked. We were not asking people to do something for us. We just wanted to see what happens when a tool or a capacity is accessible to people. That led to now what is called the Foldscope program. And it's just an absolute delight to sometimes see these pictures come through. Now, we've been running this program for the last almost 9 years. This is 3 million users and kids around the world. It's the world's largest amateur microscopy community at this point. And I love the fact that here are those 2 users in San Francisco. These are parents that are not sharing their microscope with their own child. But you have to be that parent sometimes. You have to let science travel by osmosis. And one of the powerful things about this is actually a fairly technical, powerful microscope. And I just want you to see just some of the data that comes out of it. The audio isn't playing, but I'll just continue. You guys figured out what the kid said. And then I just want you to see the data just for a second, because this will compete with some of the microscopes that are sitting in your labs as well. You don't need a cell phone with it. If you have a cell phone, you can actually use it. But on the other hand, you just visualize. You can do phase contrast, polarization. There are versions of this we've built that are fluorescence microscopy. One of the things about this is all of this data is collected by the community. There is an online platform where people share, so that's single bacteria swimming around. Those are uploads with cilia, and much of this is online, so I'm just going to skip this. This, for example, is a video from Lebanon. We started sets of programs, and let me actually just skip these sets of videos. This is what the current community looks like. The community has been growing for a long period of time at this point. And there is a pinnacle to the point of creating the sets of community that it is not a hub and spoke model. There is nobody at the center of this community. It's a peer-to-peer network. There are online platforms where people share. It's almost like an online lab notebook for the largest group of people. And sets of problems, people choose the problems that they're working on. They share sets of knowledge, and they share protocols along the way. I've only written one paper on Foldscope describing this. There are 700 or plus papers, all the way from new sets of species being described, agricultural applications, plant pathogens, all kinds of things in veterinary science, human health, ecological monitoring, lots of vector monitoring sets of programs built around these sets of tools, lots of age groups in the community. That's really the community website. And one of the things that I just want to share is that it changes when you share tools. It changes the definition that we often take for granted for who actually is a scientist. And when given the kind of access, the kind of creative ideas that people come up with. And I think if some of you have spare time, go on this site and just search for your favorite organism, and you'll find different sets of curious people engaging and exploring those sets of organisms in their ecological context. Sometimes animals have been used to see through a Foldscope. That's Moana on a sailboat. And maybe I just want to say one word about the user. This is a very special photograph to me because right in that picture is this individual named Mo Pandirajan. After English, Tamil is the most spoken language on our platform because of this one individual. In the last 6 years, one single person trained of the order of, at this point, this number is around 120,000 kids across the country. And so, this is what tells you the power of humans when combined with technology. That when I started this program, I had no idea that something like this would be possible. This person has no degree in education. He's just passionate about sharing science with people. This is the vector control program in Puerto Rico, animal diarrhea and pathogens. And again, I think this has really made me question of how to think about building these sets of programs. So I want to switch to a few other examples now. That was in the context of microscopy and education. Let's just spend a few minutes on diagnostics, and then I want to really talk about the ecological side of the story. Diagnostics are not equitably distributed. We all know that, so I don't have to emphasize on this. One of the things that we often take for granted is the kind of infrastructure for molecular diagnostics. This is something that we started 6 years ago, but with COVID, it's really accentuated in terms of thinking about, can we do distributed manufacturing of diagnostics, molecular diagnostics anywhere in the world? This is a program, most of you know that manufacturing for diagnostics is not equitably out there. And the question was, can you build a hardware and every biologic that's actually needed to make a molecular assay, say a LAMP assay, work almost anywhere in the world? That's what we started with. We spent a lot of time thinking about some of the target sets of diseases in the sets of countries, trying to understand. Most of the study sites were in Western Africa, looking at their capacity that there is vaccine manufacturing that's happening, and so it would actually be a valuable way of thinking about this. That led to this platform that we used to previously call SnapDX. Now for diagnostics under a tree, we call it D-Tree. This is a Russian doll in some sense, and one of the important aspects is in a single platform with the user, all they do is just like a syringe, press this button from one side to the other. The platform has the capacity to do nucleic acid extraction, does lysis, extraction, and amplification all in a single object with around 10 to 20 microliter of a volume of an amplification assay, all using hot water. So the joke that we have is if you know how to make tea, you should be able to run a molecular assay, which I think kind of these assays should look like that. We went through a clinical program where in 90 days, going from inventing the tool to actually testing, there's a tremendous amount of work that we've been doing on usability assays to convince that actually molecular assays can be done by people who have never been trained before for it. We've tested this for COVID. We're now transitioning much of this work to schistosomiasis to scale this. And I think the big thing that I want to mention here is The aspect has been not just to manufacture the test ourselves, but to build the entire manufacturing capacity. And that led us to thinking about, literally, in the lab, we first built 10,000 of these tests ourselves. So the lab turned into a factory yet again, because first we had built foldscopes that were around 100,000. And then now, very recently, we've actually built the entire pipeline for the synthesis, purification of the enzymes, quality testing, all in these frugal sets of platforms, all put inside a single truck. So I don't own this shipping container, but I have a shipping container on campus where the entire production pipeline for protein purification, assembly, and actually the manufacturing of these sets of... This object is inspired by a ballpoint pen, so we're actually literally using the same machines that are used for these coaxial manufacturing and molding. And this is now, with Institut Pasteur Dakar, we're actually exploring testing the first manufacturing site being in Dakar, and that's why I'm heading out there. So let me give you a few more examples. So that was around diagnostics, but sample prep is often sometimes a puzzle. I was in Uganda many years ago now, and another community health worker brought this challenge to me. And what I saw in a clinic was there was a really nice centrifuge, something that would cost $5,000 to $10,000, a high RPM centrifuge, being used as a doorstop. And I get very annoyed when I see things like that. It's like, wait a second, that makes no sense. Why would you do that? And he said, Manu, we haven't had electricity for the last 5 years at our clinic. This thing at least makes sure that the door doesn't slam a patient. It's doing something. And that kind of spun in my head. It's like, wait a second, how do you do centrifugation without electricity? And on a flight coming back, I started thinking about toys. And so, this is where you should think. This is my mechanism of the curiosity. I had an artist in my lab at that time, a circus artist. He used to love yo-yos. Does anybody know what the world record for the fastest spinning yo-yo is? No? Anybody wants to guess? Couple thousand? I think around 3,000 RPM, 4,000 RPM. That's actually pretty damn fast. But yo-yos are kind of dangerous objects. I still haven't learned how to throw it. So we started exploring other toys, and we stumbled upon this toy. This is a button on a string.
Oh my goodness.
How many of you have played with this toy? The one on the right. This also shows the age. How many of you played with a fidget spinner? Okay, that younger crowd is not here. The irony is, we had accidentally discovered the world's oldest toy. This little object has been found in all cultures around the world. 5,000 years ago, in Harappan culture, in Inca culture, in the Greek culture, it was used as a musical instrument. But nobody asked a simple question: how does this toy work? It took 5,000 years for us to ask that question. It took 6 months for us to find the answer. This is how it works. And again, one of the things is that once you can understand this, we actually had to borrow the sets of equations on how secondary loops occur in DNA, supercoiling, to be able to understand this. So I'm just going to do a quick demo for you all. And as you can see, this thing is starting to spin. And now, by optimizing these sets of parameters, we now hold the world record for fastest spinning object with human power. Not just a couple hundred RPM, we can go to 125,000 RPM. That's equivalent to a 30,000 G force when you punch in one of your centrifuges. In 90 seconds, we can get the plaque bug volume. So this is a classic test for, say, the first test you would do for anemia. So that's just raw blood and plasma extracted out of it. In a couple minutes, we can actually pull out a single malaria-infected red blood cell. So if you want to do, say, a Buffy coat or something like that. And I want to share this video of just why it's important to share tools that you build with communities. This is one of our clinical sites in Madagascar. That's a village chief testing out the tool. The irony is, I am talking in English, somebody's translating that in French, then somebody's translating that in Malagasy. There's something very important in that video. I don't know how many of you noticed this. There's only one woman in that video. That is the person sitting right behind. She is the primary health center worker there. She's also the teacher in that local school there. And in the community where only men are allowed to make the sets of, we have to have permission of the chief to work in that area. She's the only female voice in that. So again, many sets of people have been building programs around empowering women in communities. And this personally for me was a very uplifting moment to see this happen. Okay, so we open sourced this as a design. Lots of people started building on this platform. Now there are 3 or 4 tests. There is a urine diagnostic test based on this at this point. There are certain amplification assays. In COVID, we released another version of this in the context of thinking about for COVID. But then again, just open innovation in these sets of spaces allow many people to build upon ideas and platforms that you would not even think about or won't have time to build. I'm going to transition on manufacturing and a little bit more on distributed manufacturing. This has to do with period poverty. Most of you know this, that many of these, this is a medical product. From my point of view, this is an essential medical product that should exist in the world to every single person who needs it. And the irony is, and still a significant portion, 500 million people would report that they really don't have access to something so simple. And the challenge is, as climate starts to change, I don't know how many of you have looked at the numbers for cotton. Cotton is one of the most water-sensitive plants. Lots of farmers that commit suicide in countries around the world are actually because there is no water. One thing we started asking ourselves is, could we go back to the roots in plants and discover other mechanisms for manufacturing very high absorption biodegradable materials? And I love cotton candy. I had this wild idea is, you might be thinking, what does cotton candy have to do with menstrual pads? There is a link. During COVID, we started actually manufacturing an N95 grade material because there was a big shortage for it, using a mechanism that is borrowed from cotton candy machines. We built an entire manufacturing capacity to be able to go using a cotton candy machine to finally make materials and masks that utilize this. When we realized we could do this, then we transitioned and started thinking about menstrual pads. But one of the key things still was we needed a plant that would be hardy environmentally and could make a material that could match cotton in its capabilities. And that answer is actually sisal. We found that plant in Kenya. How many of you have had a tequila before? Some of you will admit that publicly. It's the same plant. It's in the agave family. It grows everywhere. It's like a weed everywhere in Africa, Brazil, India. What we realized is that very simple sets of processes that you can actually take this plant and convert this into a material that actually beats cotton at its game. So 1-to-1, you can do a comparison between this as a material. So we're now scaling this as a manufacturing platform for building all kinds of materials, but very specifically menstrual pads. This is really Alex, one of the person who has dedicated his entire life working with farmers, training them how to grow sisal. We've partnered with him to now actually make our first sisal-based menstrual pad factory. Okay, let's switch to talking about mosquitoes. I see lots of fans for mosquitoes here. I know Louis is here. Anybody else who's a fan of mosquitoes? At least loves to think about them. Okay, that's a significant portion. There are many of them. There are too many of them. We are outnumbered by a very large number. There's a friend of mine who did a calculation for how many mosquitoes might there be in Alaska. So we are doomed to begin with. Just these numbers are astronomical. We started thinking about ecological monitoring, and it occurred to us that there is a different way to this. I'm not going to say whose lab this photograph was taken in, but this was an actual lab and an actual postdoc sitting with an actual bucket of mosquitoes. And one at a time, you're picking it in, you're visualizing them, and all of us have done this. This is for identifying mosquitoes. So now I'm going to play an audio, and let's see it plays, and your job is to tell me, what are you hearing? What is that? Anybody can shout. Mosquitoes. This is, I call it the world's deadliest orchestra. This is 40th deadliest mosquitoes that transmit sets of diseases. But what I've done is I've had some musical liberty because they didn't perform together. They don't even live together. But I just want to show you that you can hear the notes. That's because mosquitoes mate in flight and they generate these frequencies, and there are biological reasons for them to not overlap. And we realized that there are 5 billion cell phones that people are walking around with, that you could just use acoustic sensors that are in your cell phones to actually record this. And that led to using a $5 flip phone. We can do real-time AI-based classification for mosquitoes. We implemented this program. We tested this in lots of places now: Puerto Rico, Ethiopia, Madagascar, Alabama. And this is a video of a kids program. We engage communities to now map their own sets of mosquitoes around, and you're going to watch lots of kids buzzing with excitement. I've never seen kids being so excited by mosquitoes. We're talking about the physics of how mosquitoes fly. This is a village in Madagascar. And these kids were involved in actually building this set of a program focused really around acoustic-based monitoring. And now with the AI sets of tools, that's getting better and better over time, and we're starting to collect more data. I'm just going to share one bit on something else that we've been building as a tool around trying to understand what does a mosquito carry and what pathogens does it actually transmit. So in the world of single-cell genomics, we kind of think about this as bitomics. What does a single bite of a mosquito contain? And now the question really was, how would you actually sample that? And we realized at that time in the lab that a mosquito is a very good pipetter, a much better pipetter than actually all of us. But we had to take advantage of that. So here is a video that Felix took in the lab. I've labeled the mosquitoes here, and watch what they do. When they bite, you see they leave that tiny drop behind. This is a type of a gel that they're biting on. That's single salivary droplet. And we realized that we could use these passive microfluidic chips. It's a piece of rubber that has tens of thousands of miniature wells that are just the right size for a proboscis and has a nanomembrane, around 600 nanometers membrane. And we can tune the stiffness of the membrane for the species that you would like. It's a mechanical filter to be able to bite through or not. And that led to this platform where we can now do, so that's the rubber chip, cost us nothing to make, single bites in each one of these wells, then we can run lots of multiplex assays. And I wanted to put this slide. We did this work with Louis, another of the viral counting of being able to count individual viruses that were in a single bite itself with Jason. And that allows us to be able to build a platform that now is getting ready to be deployed in a field setting to directly measure what many of these sets of mosquitoes might be carrying. We're also building this as an archival tool, so you don't actually have to run the assays, that you could just run the collection in the field and then go back and run the assays when a disease comes about. Okay. I'm going to switch to imaging and malaria. How much time do I have? It's 35 minutes. Oh, I'm done with time. Okay, so why don't I stop here? But I do want to say two things before I stop. If you're interested in schistosomiasis, you come talk to me. And I'm sure many of you are interested in malaria. So I just want to say this 2 words about malaria. So, you know, one context that malaria and malaria diagnostics is I brought this machine. This is the trial that we are running. I will have this machine running outside. I live in San Francisco, and I watch cars driving by. There's no person inside. Every time you see it, it's like, wow. And then I go to the clinics, and I'm out in the field, and then I watch people working for 10 hours a day, every single day, as humans, and I see this mismatch in what we should actually be solving. So 6 years ago, we started building this program, completely open source hardware and software. Now, this is the first platform that can now do completely autonomous malaria diagnostics out in the field. And I'm just going to give you a little demo for this. And while it's playing, I'll tell you how this works. So what you're watching is I've put a slide that's in real time. It's the same object that's sitting here. For a couple $1,000s, we can build this. And then this instrument, while it's imaging, every single field of view is actually doing segmentation, classification, and it's counting and identifying parasites in real time. So imaging is incredibly powerful in the sense of what we can now do and build. When we built this platform, we built it for malaria. A friend reached out in Nepal, And in 6 months, we reprogrammed the machine to do sickle cell diagnostics. Then a couple months later, we started building a program on TB. So what this is starting to become is almost an app store for diagnostics. And the last thing I want to say is actually many of these sets of tools are also now used in a research setting. And I do want to end with a comment, maybe right here. Let's actually. So, I think there's lots of tools that can be built. Unfortunately, unless we build programs where we think very deeply about who is going to actually be using the sets of tools, can we deliver them at a global planetary scale? Many of those tools will not have the impact that you might be thinking about. And ironically for us, it's really been very fulfilling as an experience to sharing tools really early, learning from that experience, and over the last 5 or 6 years, deeply thinking about a distributed approach for development and manufacturing of these tools. I'll stop here. I wish I had more time, but we can do demos outside, and if there is any time, I can take questions.